All right, today we're going to talk about stress strain curves. When we talked about failure modes, we introduced the stress strain curve that is developed during a tensile test. And today we're going to look at this curve in more detail. But before we can really talk about stress strain curves, we need to review some key material properties. So let's take a look at displacement versus force. When we apply a load to a material, it tends to deform. For example, if we pull on a rubber band, it will stretch, and the amount that it stretches is called the displacement. So if we look at these three spring experiments, in the first one on the left, there's a mass held by one spring, and the mass will cause the spring to stretch. This stretch is called the displacement. If we use two springs instead of one to hold the same mass, the mass will displace half as much. However, if we put the two springs in series instead of parallel with the same mass, the mass will displace twice as much. So the springs are analogous to materials. Every material of unit length and unit area has a springiness. So like the spring, if we double the area of the material would stretch, or essentially displace, half as much. Or you can think about it as requiring twice the force to displace the same amount. If we double the length of the material and keep the cross-sectional area the same, then the material will displace 2 times as much. So you can see how the size of the material, and not just the material type, has an influence on how much an object will displace. And we need to be able to describe material behavior that is independent of that sample size. So let's look at how we can describe material behavior without considering sample size or configuration. So deformation is the stretch or displacement caused by an applied force, and it depends on the area and the length of the structure. So to eliminate the effect of length, we use strain instead of deformation to describe the material behavior. And strain is defined by the deformation that occurs when a load is applied divided by the original length of the material. And since it's a length divided by a length, then the units, it is unitless. Deformation is also influenced by the cross-sectional area. Remember that if the cross-sectional area is doubled, the deformation is cut in half. On the flip side, if the applied force is doubled, the deformation is increased by 2 times for the same cross-sectional area. So in order to eliminate the effect of force and area when describing a material, we use stress. And stress is the applied load divided by the cross-sectional area. Cross-sectional area is the area over which the force is applied. If the force is applied axially, like in tension or compression, then we use sigma to represent stress. However, if the force is applied perpendicular to the area, as in shear, then we use tau to represent stress. The key here is that stress is a material property, and it is independent of the sample tested. So if I test multiple samples of the same material, they can all have different cross-sectional areas, but they will all fail at essentially the same stress. Not the same load, but the same stress. The larger samples will take a higher load to fail, but when you take the load at which it fails divided by the cross-sectional area, the stress should all be the same. And the units for stress are force divided by length squared, so it has units of pressure, such as pascals or psi. Now here's a visual representation of the difference between axial and shear loading. In axial loading, the force is applied either in tension, which is shown here, or in compression, so we would just switch the direction of the arrows or the force that's applied. In shear, the force is applied in 2 directions, and the cross-sectional area is the area that is perpendicular to the applied force. So in the images on the left, the cross-sectional area for both loadings is the same, and it is this rectangle here. On the right-hand side, the cross-sectional area in tension would be the area of this circle. And then in shear, where we're going in opposite directions, we're shearing, and this is the cross-sectional area, that little rectangle of the board there. So now that we know what stress and strain are, they help us to describe the material behavior independent of sample size. So let's look more closely at some failure. So tensor failure is, again, when we pull on something, and it typically stretches and then causes the cross-sectional beam of the area to become smaller and smaller until it eventually breaks. So to test materials in tension, we create these dog bone or barbell-shaped samples, and then we put them in a load cell with vice grips and slowly increase the load. The reason that we use the dog bone shape is so that the stretch and failure will be localized in the middle of the sample and not at the grips. We already know that if the cross-sectional area is smaller, the load required to stretch and eventually break the sample will be lower. So the failure is contained to the middle of the dog bone when we use this shape. As the load is increased, we record the applied load and the displacement. We know that load and displacement are dependent on sample size. So to get the material properties, we'll divide the load by the cross-sectional area to get stress, and divide the displacement by the original length to get strain. We then plot stress versus strain. And when we do this, we get a plot that maybe looks something like this for a ductile material. At first, when we first start pulling, we'll have a linear region. If we were to stop the test anywhere along this region, the material would return to its original length. This is what we call the elastic region. Once it reaches the yield point, the material will begin to yield or deform permanently. And we can estimate the yield stress from the graph, from where this goes from linear to nonlinear. Now, in many cases, we don't want our material to deform, so we might design to the yield point. So let's take a look at an example. Here we have a steel bolt that is 1/2 inch in diameter, and it is used to mount a sculpture to the ceiling in a building's lobby. If the yield point of the steel is 50,000 psi, we're asked to find how much weight can be supported by the bolt before it yields. So remember that stress is equal to the force divided by area. Well, in this case, our force is weight. So it's the weight over area. And we're trying to solve for weight. So we can rearrange this equation and say that the weight is going to be equal to the yield stress times the cross-sectional area. So the yield stress is 50,000 pounds per inches squared. And then the area, well, we want the cross-sectional area of that bolt. It's a circle with a diameter of 1/2 inch. So the area is pi r squared. So we'll say multiply by pi. The diameter is 1/2 inch, so 0.5 divided by 2 squared, and that's inches squared. So the inches cross out, and if you multiply this out, you will get 9,817 pounds. So that is the load at which this bolt will yield in this scenario. Now, rarely, if ever, do we actually want to design right up to the yield point. So if the typical load for a bridge is about 20,000 pounds, I certainly don't want to drive across if it were designed to yield at exactly 20,000 pounds. That really would not give me much comfort. So we use a factor of safety so that we design for multiple times stronger or stiffer than you actually need something to be. As an engineer, sometimes this is your decision. Other times there are legal regulations that tell you what factor of safety you must use. But as an example, if the factor of safety is 2, it is designed to handle twice the load that is expected. Typical roof trusses will have a factor of safety of about 3. So if we go back to that same 1/2 inch steel bolt, and we know that the yield point is 50,000 psi, same as before. How much weight would you allow it to hold with a factor of safety of 4? So again, we have sigma is equal to force or weight divided by area, right? And so our weight is the yield stress times the area, which is pi times 0.5 divided by 2 radius squared. And so the weight is 9817 pounds, just like before. But if we want to design it with a factor of safety, we are only going to allow it to hold 1/4 of that. So if we take this weight and divide it by 4, then we're going to say that this is only allowed to hold 2,450 pounds. So that would be our design limit with a factor of safety of 4 for that bolt. So let's look back at the stress strain curve. This area where the stress versus strain are proportional before we reach the yield point is where it's in elastic deformation. The slope of this linear segment is called the modulus of elasticity. This modulus can be thought of as the material's stiffness or its resistance to deformation. The greater the modulus, the stiffer the material, and essentially the smaller strain you'll have for a given stress. An elastic deformation is not permanent. The material will return to its normal shape once the applied load is removed. We can calculate the modulus of elasticity as the change in stress divided by the change in strain in this linear region. And since strain is unitless, modulus of elasticity has the units of pressure, or psi, or pascals. Again, keep in mind that the stiffer the material, the higher the modulus, and thus the slope of this curve. All right, so let's look back at that same bolt from the previous example. Now, if the bolt is 10 centimeters long, how much will it stretch if a 5,000 pound sculpture is hung from it? So remember that modulus is the change in stress over the change in strain. So if we rearrange that, we get the change in strain is equal to the change in stress times the modulus. Well, our original stress and strain are both equal to 0. So really, we're just going to talk about what is the stress and strain at that point, since we're starting at no load. Okay, so we can first calculate sigma, the stress. Again, that's going to be the weight divided by the cross-sectional area, where my weight is 5,000 pounds. And my cross-sectional area is the pi r squared, so pi 0.5 divided by 2 squared, and that's inches squared. And so my sigma, or my stress there, is 25,460 psi. Okay, and now we know what the modulus is. So I can say, we can plug that in here. So my change, or the change in the stress, or the new stress, strain, sorry, is going to be this stress, 25,460 pounds per inches squared, times, I did that, let's see, this is not correct. This would be divided by, sorry about that. So strain is the change in the stress divided by the modulus, not multiplied by the modulus. Let me go back. Modulus is equal to delta stress over delta strain, and so if I move that over here, delta strain is equal to delta stress, or the stress divided by the modulus. So we take this and divide it by the modulus, which is 30 times 10 to the 6 pounds per inches squared. And if you multiply that out, you get 8.5 times 10 to the negative 4. And the units will cross out. Remember that strain is unitless, so that makes sense. And then, if you remember, Strain is defined as the change in length divided by the original length. So if I want to know how much the bolt stretches, I want to know what delta L is, the change in length. So that's going to be the strain times the length. Strain is unitless, so it doesn't matter what units I put here. I'm going to get this answer in whatever units I use. So 8.5 times 10 to the negative 4 times my original length, which was 10 centimeters. And so the change in length will be 0.0085 centimeters. So that is how much the steel bolt will stretch when a 5,000-pound sculpture is hung. Okay, so now once we reach the yield point in our stress strain curve, the material then begins to go into the plastic region. And beyond this region, beyond this point, all of the deformation is permanent. The material will continue to stretch until it eventually fails. The ultimate strength is the peak stress. So we can read that from this curve. There's my ultimate stress. So if we go back to that same bolt, that 1/2 inch diameter bolt used to mount that sculpture, how much weight could it support before it actually breaks or ruptures? Not before it yields, but before it ruptures. So we use that same equation, stress is equal to force or weight divided by cross-sectional area. And so we want the weight is going to be the area times the stress. And our rupture strength or stress is 75,000 pounds per square inch. And my area, again, is pi r squared, so pi times 0.5 divided by 2 squared. And if we multiply that out, that'll be 14,725 pounds. So this is how much load the bolt can hold before it ruptures. And this is with no factor of safety. So in the plastic region, the ductile material will experience what we call necking. And that's when the cross-section decreases at a relatively fast rate because large amounts of strain are localized. Here the results are permanent deformation. When we release the load, it maintains its shape. It doesn't go back to its original length. And this is going to occur in the middle of the specimen because we designed to do it that way by making it the narrowest part of the test. So again, here's kind of my necking region. So now one thing that I do want to point out here is that we are plotting and calculating engineering stress and not actually true stress. Engineers like to work smart, and plotting the true stress is considerably more work for little to no added benefit. Remember that the stress is the load divided by the cross-sectional area. Stress is equal to the load or the force divided by the cross-sectional area. Well, as the sample stretches, right, that cross-sectional area gets smaller and smaller. And so the true stress is the load divided by the actual cross-sectional area at that point. When we calculate engineering stress, we use the original cross-sectional area for all the stress values. We don't take into account the fact that it's getting smaller and smaller. And this makes the work a lot simpler, as trying to measure the cross-sectional area as the sample stretches is very difficult and time-consuming, and really the results just don't justify the added work. There is generally very little difference between, especially when designing in the elastic region or the beginning of the plastic region, so the added effort isn't needed. And also we typically apply a factor of safety, so it's really not that important that we're using engineering stress versus true stress. But if we did use the true stress, if we did plot it, it's going to look something more along this line. The stress actually doesn't ever really decrease. All right, so far we've seen how to calculate modulus and how to decipher yield strength and ultimate strength from a stress strain curve. We can also get the rupture strength in the same way, just reading it off the graph. Here's my rupture strength. And then there are a couple other properties that we can also estimate using the stress strain curve. The first of these is the modulus of resilience. This is the total energy that can be absorbed per unit volume without creating any permanent deformation. We find this value by integrating the stress strain curve from 0 to the elastic limit. Okay, so if we're designing within the yield stress, most of the time, we don't want anything to change in shape. This would be where we want to have, resilience would be where we want to have lots of amounts of stored energy in a modest amount of material. Someplace like a knee joint where you're jumping or running or walking, or maybe clicking on a pen, or a spring that needs to absorb bumps as you're landing, something like that. That is a place where we would want high resilience. Modulus of toughness can also be estimated from the stress strain curve, and this is the ability to absorb energy in plastic deformation. So it's absorbing energy as the material fractures. And we can estimate modulus of toughness by calculating the area under the entire stress strain curve. And there's a formula there that can be used to kind of help you to do that. And toughness is usually a premium where things are designed to fail while absorbing energy, such as a bumper in an automobile accident or in safety equipment. So as a recap, toughness is how much energy is absorbed before fracture and while something's breaking, and resilience is how much energy can be absorbed and returned without permanent deformation. So think more like a spring. Okay, so let's take a look at an example here where I have these aluminum rods, and modulus is given as 10 times 10 to the 5th psi. We have the yield stress and ultimate stress in tension, and the yield stress and ultimate stress in shear. So the first question is asking us, what is the minimum diameter to keep this aluminum rod AC from yielding in tension? Well, in order to do that, I first need to know what is the load that is in that rod. So to do that, I am going to first do a free body diagram. So I have my 10,000 pound load, and then I have a force B, and I have a force, well, I guess this would be AC and AB. And this angle here is 45 degrees. Well, this means I have three forces in equilibrium. So they are concurrent forces. So I can use the sum of the forces in the y direction is equal to 0 to solve for AB. So I'll have negative 10,000 plus AB sine of 45. And if I solve for that, I get AB is equal to 14142 pounds. Once I know that, I can do the sum of the forces in the x direction. So I would have 14142 cosine of 45 minus AC is equal to 0, and so AC is equal to 10,000 pounds. So that is the load that is developed in this aluminum rod. And so if I want to determine what is the minimum diameter to keep that rod from yielding in tension, I need to say, okay, well, the yield stress is equal to the load divided by the cross-sectional area. And so my area is going to be equal to the load divided by the yield stress. Well, my load, I just found out, was 10,000 pounds. And my yield stress is 43 pounds per inch squared. And that will give me my cross-sectional area. And if I calculate that out, I get 0.3289 inches squared. Now the question asked, what is the minimum diameter? And so I'm going to take that and set it equal to pi r, d divided by 2, how about squared? Pi r squared, or d divided by 2, and if you set this equal to that, you get the d is equal to 0.647 inches. The next question is asking what's the minimum diameter for tensile yield. At the minimum diameter for tensile yield, will the rod fail catastrophically in tension if the load is increased to 12,000 pounds? So in other words, if I'm using this diameter, will it fail catastrophically in tension if the load is increased to 12,000? We know that at this diameter it will start to yield, but will it actually fail in tension? Well, let's see. In order to determine that, I need to see what is the stress that's developed. So the stress is going to be the 12,000 load divided by that cross-sectional area, which is 0.3289. So this is my pounds, this is my inch squared. And so the load divided by the cross-sectional area gives me 36,485 pounds per square inch. So I want to compare that to what is the strength, in tension, the ultimate strength. So the ultimate stress in tension is 53,000. Well, this is less than 53,000 psi, so it will not fail in tension. It will yield, but it's not going to fail catastrophically. So if we go above the 10,000, we know it's going to yield, but it won't fail. And then says using a factor of safety of 2, what is the max load that AC rod could withstand before it shears? So let's see, max load. So we'll use the ultimate stress in shear. So in the stress in shear is going to be the load divided by the cross-sectional area. So we want to calculate what is this load. We're going to assume that it's the same area, and we want to use a factor of safety of 2. So if we're using a factor of safety of 2, we want to essentially say we're only going to allow it to go up to half that strength. So I'm going to take that 39,000 psi and divide it by 2, and then multiply it by this area, which is 0.3289 inches squared, in order to get the load. And if I calculate that out, my load is 4,317 pounds, and that would be the max load that this rod could withstand in shear with a factor of safety of 2.